Yes. So, okay, today we will talk about Wi-Fi, and I guess there are several reasons why we do this. One is to introduce a little bit on networking over wireless medium, and then also because Wi-Fi is such a ubiquitous thing, it's all over the place, right? So it would be nice to know a little bit on how it works. Short review where we're standing. We're talking about local area networks. So these are typically small networks, and the protocols for these are placed in the link layer. So we have the OSI here, and we have the IEEE stack on the left. So if you remember, we talked about the link layer control, and then on this MAC, which is also known as Ethernet. Okay, so this is Ethernet. And now we will talk about Wi-Fi today. There is another very similar standard to 802.3, also called Ethernet. DICS Ethernet or Ethernet 2, if you like. It's actually an earlier version than the IEEE Ethernet, and it's still very heavily used in practice. So both of these standards coexist, and sometimes they could also coexist on the same local area network, actually. We also talked about last time on how to connect local area networks together. So if we have several of those, we can put them together with using transparent bridges, which is a type of switch. By doing that, these bridges are transparent in the sense that they don't need any configuration by the host or the network administrator. They basically are self-configuring, and what they need to do then in order to operate is to create forwarding tables. And the reason for this is that the switches have a number of input ports, number of output ports. So when a frame arrives on an input port, the bridge needs to know what to do with this, whether it should be forwarded out on all the other ports or just one of the ports or whatnot. And this is done with these forwarding tables. And we talked about backwards learning on how the bridges can figure out what to do by simply listening to the traffic which is going on the attached local area networks. We saw that this works great, but it works not so great. It doesn't work when we have local area networks which are connected with bridges that have loops in them. So if we have one local area network here, another one here, and if we have two bridges connecting these local area networks, something that one would like to have, for instance, if for redundancy reasons or not. And then there is a loop here. So if this is LAN 1 and this is LAN 2. These loops here are not good for backwards learning. So with this spanning tree protocol, we can basically disable logically these physical links and then avoid that we have loops. And then the backwards learning works. So this spanning tree protocol in conjunction with this backwards learning makes it possible for us to just connect a bunch of local area networks together using switches and then just wait until it works. So it's rather nice, actually. Okay, but today we will talk about wireless communications or wireless data communications. So why do we want to do wireless? Well, basically for two reasons. One is because of convenience, and the other thing is because of necessity. So convenience, it's nice to have wireless stuff. It's nice to have wireless earphones, for instance. You don't need to, because typically you have your telephone or whatever you're listening to attached to you, so you can just draw a cable between your earphones and the phone. But it's nice. It's convenient to have wireless, and sometimes you have to do it. For instance, when you want to communicate when you're on the move, when there is mobility, then we are forced to do wireless because you can't draw cables. So, so this is clearly something that we would like to do. Now, so what are the challenges, and in particular compared to what we have done up to now? Well, one challenge is because we communicate over wireless, then the receive power falls off very quickly with distance. So that's one problem. And typically one says that the receive power, PRX or D here, depends on, according to this expression, where D0 here, D is the distance between the transmitter and receiver, and D0 is some reference distance. So you can just pick that what you like, maybe 1 meter, 10 meters, or something like this. And then one sees that the receive power falls off with D to the power of negative alpha. So this negative alpha is known as the path loss exponent. And this one depends very much on the propagation environment. So if it would be free space, where if the universe consisted of a transmitter and a receiver, then the power would fall off as the square of the distance. So if we would draw something using that equation, we see that if we typically one measures receive power in decibels because it's a convenient metric. So if we take PR Rx at some distance, and we would like to measure that in dB units, then it's the 10 log 10 of the received power in linear units. And then one can also divide this by having some other reference power than 1 watt. But here we divide this by 1 watt, and then we get this in what's known as dB and then W for 1 watt. If we measure this in milliwatts, it's dBm, M for milliwatts. But it's not important for our discussion here now. But anyways, if it's like this, then by just plugging in the expression for the received power here, with some simple manipulations, we can get this to be the received power at the reference distance minus 10 times alpha, the log 10 of D divided by D0, like this. And if we would draw this, we have a distance on this axis and the received power on this axis. We need to select some reference distance, D0. It's not important exactly what this is. We can think of this as 1 meter perhaps. And then if we draw this in log scale, this axis, so this is D0, this is 10 D0, and this is 100 D0, then this equation tells us that the received power in dBW is then a linear function of the log of the distance. So it will be a straight line like this, where at the reference distance here, we have the received power at D0 in dBW, like this. And then it falls off linearly here. And the slope is equal to minus 10 times alpha dB per decade. That is, if we increase the distance by a factor of 10, then we lose 10 alpha decibels of received power. Okay. So then at the reference distance, at the distance 100 times the reference distance, we get another 10 alpha in power loss in dB scale. So to put this in a little bit of a perspective, suppose alpha is equal to 2, then 10 alpha, of course, is then 20 dB per decade. So with each time we move a distance which is 10 times the reference distance, we lose 20 decibels of receipt power. And then 20 decibels is a factor of 100. Okay, so the power loss from here to here is 100 in linear scale. And then another 100 here. So from here to here, it's a factor of 100 times 100, that is 10,000. Okay, so say that from 1 meter to 100 meter, we lose about 10,000 times of the transmitted power. Okay, there's quite a lot of power loss, right? So if this is 1 watt, which is a tremendously high power, but just to get this, then this will be 1/100th of a watt, and this 1/10,000th of a watt. Okay, so we lose a lot of power here. And on top of this, if one looks, this is what the power decreases as on the average, but there is also small variations that if we move just a tiny bit, like a wavelength or something like this, then the receipt power can actually varies quite a lot around this, and this is known as fading. And the fading comes from constructive and destructive interference patterns in a complex environment due to multipath. Okay, so the receipt power is it is one of the big problems in wireless, to make sure that we have enough receipt power in order to transmit data. And it's also a problem that it varies quite a lot when we just move a wavelength. And at 1 gigahertz carrier frequency, the wavelength is about 30 centimeters. So the power varies quite dramatic as we move just 30 centimeters. And if we go up to 3 gigahertz, is 10 centimeters. 6 gigahertz, 5 centimeters, right? So the higher up in frequency, the more quickly the power varies as we move through the environment. Okay, so this is one of the main challenges with wireless communications. Now, since the signal strength, there could be a big difference in transmit and receive power. So, I mean, if this is the transmit power, and this is the receive power 100 meters away, a radio receiver, which is here, would see this receive power, but it will also transmit at a power which is 10,000 times more than what it received. So this imbalance between transmit and receive power makes it more or less impossible to do full duplex communications. So wireless is typically half duplex. Okay, and it also makes it problematic to do collision detection. Is more or less impossible. Okay, other problems with wireless is that the radio spectrum is a shared medium. Okay. And that means that we need multiple access, medium access control. Okay, we cannot do the same trick as we do in wired systems by just buying a device like this and then plug in cables in this, and then we suddenly don't have a medium access control problem anymore. In wireless, there is no switch for that purpose. Another problem with radio signals is that they're much easier to listen to because they're not confined to a cable. So it's very easy to listen to radio channels compared to listening to signals on a wire, which means that the security problems from that perspective is more problematic. And it's also much easier to jam signals in wireless than in a wired medium. And to top everything up, the radio spectrum is quite limited. So it's sort of like it is a natural resource, and it's heavily regulated. Okay. So there are only problems with wireless, right? But it's so good that we want it. But we need to, there's a lot of engineering going into wireless to make it efficient and good and so forth. When it comes to mobile access to the internet, there are basically two major families of standards that support this, and that's Wi-Fi, the 802.11 standards, and then the cellular standards like 3G, 4G, 5G, and so forth. But we will talk about Wi-Fi today. So Wi-Fi, the 802.11 standards, they had a pretty slow start at the beginning. What made it happen from the beginning was that, remember, the spectrum is regulated. So basically, it's in Sweden there's the Post and Telestyrelsen who decides about who can transmit in what frequencies. And you typically have to pay for this, or you have to be the military or somebody like this that basically gets spectrum from the state. But what they did in the US in 1985 was that they said, okay, we will give some spectrum that anybody can use as long as they follow some basic rules, right? So then this is called unlicensed spectrum, in particular in these frequency bands. And if you know about Wi-Fi, you know that this is where many access points are operating today, around 2.4 gigahertz, and also around in this 5 gigahertz band. Okay, so these bands are heavily used for Wi-Fi today, with some variations. I mean, there are regional variations, so something that is allowed to transmit here might not be allowed to be transmitted in France exactly, right? And there will be other small differences as you move around in different countries. Anyway, so this started then in 1991. One started work on this first version of Wi-Fi, and the first version was released in 1997. So it took a long time before it actually was published. And then it sort of slowly gained some traction, and now it's a tremendous development. So the development of this is much faster, and the number of Wi-Fi access points and devices is huge. So today 802.11 has evolved in this super complex and large standard. And the last document is about 3,500 pages. Okay. Now, out of these 3,500 pages, maybe 2,000 pages is not used. Well, maybe I'm exaggerating, but it's sort of like a standard which has evolved over time. So it keeps all the old stuff, even though nobody is using it. It's used mainly for backwards compatibility, and also because it's, well, I don't know why you keep something that is not used, but sometimes it's used somewhere in some obscure deployment, and you still want to keep it like that. Anyway, since the development in this area is quite fast, then whenever you read about Wi-Fi in a book, it's likely to be outdated. So in the book, there is some stuff which is not relevant, right? Or at least not the latest, greatest. But that's how it is. Okay, so here's a screenshot of my laptop when I looked at, okay, the Wi-Fi status a couple of years ago, I think. So it has an information here. It's something about SSID, security, BSID, channels, country code, RSSI, noise, blah, 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 blah. So let's figure out what these things mean and how this is supposed to work. Now, first of all, we need a few definitions or terminology for this to work. And this is the drawback with practical stuff, is that there is a lot of jargon and acronyms and so forth, and it can easily become overwhelming. But we actually need to go through a few things here. Otherwise, it's hard to be precise about things. But there is something called a basic service set, and that is abbreviated BSS. And this basic server set, which I will explain in a second, is identified by a BSS ID. Okay, so that makes sense. So a basic server set is a group of stations, and a station is like a Wi-Fi device that has agreed to coordinate their access and communicate with each other. There are infrastructure networks, and infrastructure networks are those who have an access point. So there should be an access point, perhaps not in this room, but somewhere here close by, where my laptop is now connected to, and your phones probably also. Okay, this BSS ID for this access for this infrastructure network is the access point's MAC address. So if we go back to here, at this moment when I took this screenshot, my laptop was connected to a BSS whose ID was this. So this is the MAC address of the access point at that particular point in time. You know, if I go somewhere else, still being connected to EduRoam, I will probably get another access point, and this would change. Okay. Now these BSSs, basic server sets, they are physically located in an area. Okay, we can think of this maybe as a, you know, like a building or a floor, a couple of rooms in a building which is served by an access point. This is called the basic service area. And stations in a BSS, they can communicate with each other. And several BSSs can exist in the same area. You know this. When you pop up your phone or laptop, you see there's a bunch of Wi-Fi networks available. And indeed, the same access point could serve several BSSs at the same time. Maybe you have your home network and your guest home network in the same access point. For instance, that's quite common. All right. Now, an extended service set is then identified by an SSID. So if we go back here, so we see SSID was EduRoam. Okay. So this means that I'm connected to EduRoam, and EduRoam is an extended service set consisting of many basic service sets, each basic service set served by one access point. Okay. For me as a user, I don't care really which access point I'm currently hooked up to. It's more important for me to know what network I'm hooked up to. And network is this extended service set. Okay. So an extended service set is identified by an SSID. This is what we call network name, perhaps. So multiple BSSs are then these access points are interconnected by some distribution system, DS, which is typically like an Ethernet LAN. Okay, so I mean you have behind the access point you have switches and cables and whatnot to connect the different access points, and that is the distribution system then. All right, and then we have portals attached to this distribution system, which provides access to the internet. So somewhere there is a router, basically connect to that Ethernet LAN, and after that router there is maybe an internet service provider or whatnot to provide access to the internet. Okay, well, I'll get back to this. So pictorially, a basic service set could be something that also works outside without an access point, where we work in something called ad hoc communications. And here is a bunch of Wi-Fi nodes here got together and said, hey, let's form a network. And you could do that without an access point, and sometimes this is useful. We will not talk so much about these independent basic service sets. Except by mentioning that you don't necessarily need to form a basic service set in order to communicate over Wi-Fi. For instance, traffic safety with 802.11p is an example where these nodes could be vehicles and they can communicate with each other without forming a BSS at the beginning. And the reason for this is the reason why you want to do this is because it takes a little bit of time to form these networks. And if nodes are moving in and out and so forth, that could cause some intolerable delays. Anyways, there is also then ad hoc communication possible with 802.11 when we communicate outside the context of it's called outside the context of BSS or OCB. Okay. We will not talk more about this at this lecture, but just to show that Wi-Fi standards actually have many different modes and so forth. And when one talks about Wi-Fi, one typically concentrates on infrastructure because this is what people are typically used to use in their phones and laptops and so forth. So infrastructure, what is that? Well, it's when you have these particular devices called access points. So this is a Wi-Fi device that serves a certain physical area. So here we have a basic service area, okay, which is then served by this access point, number one. And we have another basic service area here, which is served by some other access point, AP2. These access points are then connected with this distribution system. So this could be like a wired Ethernet, very often is. And then attached to this Ethernet LAN, there are these portals, which is devices which leads out to the rest of the world, perhaps to a server or to the internet. Now, these devices here, A1 and A2, these are two stations which are associated with access point number one, and B1 and B2 are two stations which are associated with access point number two. But these can communicate with each other, but only in different modes. So two stations which are in the same basic service area, they can communicate directly with each other if they like. More typically, they go through an access point. But when you go through an access point, you can also go over the distribution system to reach stations in another basic service set. So this is how data is typically transferred in these systems. Any questions so far? No? Okay. So let's continue then. Oh, yeah, and of course, the most common type of communication, I guess, is from an access point to the internet. Sorry, from a station via an access point via the distribution system out on the internet, and the opposite, right? From the internet, it goes through the portal into the LAN, finds the access point, and then goes back to the station. So that's probably the most common type of communication. Yeah. So stations within a basic service set, they can communicate directly with each other. Through the distribution systems, one can also communicate with other stations. So this distribution system, they provide services, and what they do is that they provide a service to transfer what's called MSDUs, MSDUs, which is short for MAC SDUs, and SDU is service data unit, MAC is medium access control, right? So these service data units are actually LLC PDUs. Okay, there are many acronyms here now, but if you remember, LLC is on top of MAC layers in the IEEE standards. So whatever data comes from above, maybe an IP packet, it will then be encapsulated into a PDU, LLC PDU, which will be encapsulated into a MAC SDU. Okay, so the distribution system provides a service for transmitting these. Okay, this is the now it gets very messy on this slide, but this is the MAC SDU. Okay, so it transfers these between access points, between portals and access points, between stations in the same BSS. And we'll see this creates some interesting addressing problem in Wi-Fi. Oh, not problems, but one has to have a particular type of handling addresses. Okay, and ESS then looks like a single BSS for the LLC layer, which is above a station that belongs to that ESS. So for the LLC, it's unaware of the basic service sets and so forth that together forms the ESS. Okay, so now before anything can happen, when you put on your laptop, it needs to somehow identify a network and then connect to it. Okay. The first time you do that, you typically put in a passcode or something like that. But once you've done that, it's sort of automatic. But what happens is that before a station can start to use the network, it needs to do two things. It needs to authenticate itself and then associate it with an access point. So this authentication is basically that it's a way for the station, the laptop, to prove its identity to the network. Okay. So a station would like to establish its identity with an access point. And this could be done in different ways, either by using a pre-shared key. Okay, so we have a key, local key here, and a local and a key in the access point that we somehow agreed upon that everybody who has this key can authenticate themselves to this access point. So this is typically what we have in home networks, where you have a network key that is printed on the backside of your Wi-Fi router. Should maybe change that, but anyways, that's what it is, right? So it's pre-shared in that sense. Now, and the second thing one needs to do, or the other option, is to basically connect to the network without a key. So these are these open Wi-Fi networks you see. You can simply connect to them without having a password at that point. Okay. Then the second thing one do is to associate. So after authentication, a station register itself or associates itself with an access point in order to gain access to the network. So that's step number 2. Currently, it's recommended to use what's known as WPA2, which stands for Wi-Fi Protected Access version number 2, when doing this authenticate and association stuff. When there are many different ways one could do that, but this is the currently best known. So there are two versions of this, the personal one or the enterprise version. And the personal one has this pre-shared key, which is printed on your Wi-Fi router on the back side. So this is very common in home networks. But the enterprise one is a little bit more complex. It's more secure, but more complex authentication association process, which is then common in, not to a big surprise, in enterprise networks. Right? So if we go back and see the screenshot here, you see here that the security here was indeed WPA2, but enterprise version of this. And this is because eduroam is like a professional or enterprise type of network. So when proving this laptop's identity to the network, this is done by basically connecting to this system with no key and then associate, but actually in the association process, one has to communicate with the authentication server and so forth. There's a bunch of stuff going on in the background here. But one can, to make it a little bit simplified, one can say that one should always have security on one's network, and the one should use today is WPA2. Next year is probably WPA3, I don't know, but it is possible because these are not 100% error-free, because nothing is 100% error-free. So one always finds security problems and try to fix them. But these are the best we know today, so one should use them, right? Then we can reassociate service, and that is when there is a service called reassociation, and that happens when we move from one access point to another, and we still want to be connected to the same network. So this typically happens without user interference, and then one can associate with an access point also to terminate this. Okay, so now suppose we have an access point. We have a bunch of laptops, telephones. They have authenticated themselves. They associated to this access point. Now it's start time to communicate. And communication is then coordinated by the IEEE, by the medium access control. So this layer has then responsibility for channel access. So we will go through how that works. And on also addressing and formatting and error checking and so forth. And then fragmentation and reassembly of these service data units also. And then there are some management services for moving from one access point to another access point, and then also to put nodes into power save, which is also quite important for battery-powered devices. Okay, so there are two main communication services in 802.11. One which is a contention service. Contention means fight, basically. So where we fight for access or compete for access. And then there is a contention-free service. Now this contention-free service is not used as far as I know. So let's forget about that one and then just talk about the contention service. So, but anyways, if one would draw a protocol stack on this, we have the physical layer on the bottom, and then we have this service which called distributed coordination function, DCF. Okay, and on top of that there could be something called point coordination function, and this one is for the contention-free service. But since this is not used, let's forget about that, and we concentrate on this thing. So basically we have MAC layer service data units coming up and down here. Okay, so we have on top of this LLC. So anyways, it goes up and down like this, and then it pops down into this layer here. So we can think of this as the MAC layer actually. And then we have a physical layer also. Let's concentrate on the MAC layer and medium access. So 802.11 use carrier sense with collision avoidance. Okay, so it's important to stress avoidance here, not collision detection. Collision detection, if you remember, was used in Ethernet, wired Ethernet, at least in the beginning before we got switches. After we have switches now, there is not the medium access control problem anymore because that's taken care of by the switch, and therefore even if collision detection is in the standard, it's not very often used. Now the reason why we don't do collision detection, is because of this power difference that we talked about earlier. It could be that the receive power and transmit power could could differ with 100 dB easily. And 100 dB is when the transmit power and receive power differs with a factor 10 billion, 10 to the power of 10, right? So, I mean, think of it that your receive power is 1 watt and you receive 10 gigawatts, okay? Or you transmit with 10 gigawatts. So you can see the problem here in listening to the channel at the same time as you transmit. Basically, you would burn out your receive circuit if you're trying to listen while you transmit. Okay. Nobody will be happy with that. Okay. So there are experimental full duplex devices where you listen and talk at the same time. but this only works when the power difference between the transmit and receive power is relatively low. Okay. When it becomes very low, it's feasible to do this, right? But it all has to do with the distance between the transmitting and receiving node. If they're very close to each other, then one can tune down the transmit power so that the power difference is not so huge. But this is experimental, so the general rule, I would say, is that it's not used. For sure, it's not used in Wi-Fi or in cellular at the moment. Carrier sensing in wireless is not perfect, and the reason for this is that even though we are in the same basic service area, the transmit, if we are on two opposite ends of it, then the receive power could be weak, and it's not sure that we can hear an ongoing transmission. So carrier sensing is not perfect. Okay. So we will touch more on that in a few slides here. So how does this work? The medium access. So we then concentrate on DCF, which is this contention-based service. So it provides best effort data transfer. So no guarantees, no reliability. It tries to do its best, but no guarantees. All stations contend for the access to the medium. So the basic idea with this CSMA CA is the following. It's a carrier sensing, so basically means that sense the medium during a particular time interval, and this is known as the DIFS, which stands for the Distributed Coordinating Function Interframe Space. Okay, that will come on the exam, exactly this wording. No, it will not, right? But that's what everybody says it diffs, okay? But this is what it is, really. Okay, so this interframe spacing is crucial to the operation of the protocol, as we will see. Anyways, during this time, if it turns out that the channel is idle, if it's busy, the medium is busy, then we defer, which is the same thing as we wait until the current transmission is finished, and then we go into back off. If it's idle, then we transmit, wait for an acknowledgement, wait for another diffs, and then we back off. Okay. So if I'm the only station that's interested in transmitting a frame, and that frame becomes available at this point in time, so what do we do then? Well, first of all, we listen to the channel for diffs. If the channel is not busy, then we transmit the frame, wait for an acknowledgement, and once we receive the acknowledgement, we're done transmitting that frame, and we're now ready to transmit the next frame. Before we can transmit the next frame, we have to wait first for the diffs, and then back off a little bit until we can transmit the next frame and acknowledgement. We'll see more detailed timing diagrams of this in a second. But this is the main idea, that we are a little bit cautious in accessing the medium. We always listen for diffs before we do anything. And if nothing has happened here, then we can transmit. And then we wait for another diffs before we can do something. And since we are a little bit cautious about accessing the channel, we always do back off until we start to transmit the next frame. Okay. So it's a little bit on the line of non-persistent CSMA, a little bit. Okay, but let's do this first. So let's look at transmission of frames with acknowledgements, which is the standard way to do things. So we have a source, we have a destination, and then we have other nodes. So at some point in time, the source gets a frame from its LLC layer above, right? And then it listens for diffs. If nothing is there, then it transmits a data frame. Then another node which became ready, that is, got a frame from its LLC layer at this point in time, would then listen to the channel and then hopefully hear the data frame which is ongoing. So that station will wait, defer access, that is wait until the ongoing frame transmission has been completed. So what is meant by this is that we have to wait until both the data frame has been received and an acknowledgement for that has been sent. Okay. So the destination will hear this data frame, and then at this point in time it has a short period of time before it needs to transmit its acknowledgement. It has to be transmitted after SIFS. Then SIFS stands for short interframe space. And then it transmits an acknowledgement, and then everyone needs to wait the diffs after this ACK frame has been transmitted. Okay. So the other node needs to wait until this point in time, for sure. Now, suppose that the blue user here, the source, has transmitted one frame. It has typically transmits several frames in a row. So it typically has a frame to be transmitted here, and then at least one of the other nodes has a frame to be transmitted here. But before any of these access the channel, both of them go into backoff. And backoff is random, it's a random delay. So the source will draw a random number, R, which happens to be 6 slots in this example. I mean, it could be anything, right? But in this time it was 6 slots. The other one draws a random number 4. So it has to wait for 4 slots. So then we wait for a slot, both of them do, 2 slots, 3 slots, 4 slots. Now after 4 slots, the source here has still 2 more slots to wait until it can access the channel. But here the backoff counter has gone from 4 to 0, which means at this point in time, this other node is able to transmit its data frame and wait the SIFS and then receive an ACK for this, according to this, the same type of exchange as here. And then the other node needs to pause its backoff during this time, because it will then see that the channel became busy during this time, and then wait the diffs and then resume backoff. So it will count down 1, 2, and then transmit its data frame. So this is how things are coordinated. Any questions? So SIFS, this short interframe space, is smaller than a diffs. Okay, so this time is smaller than a diffs, and that is to give the ACK frame priority over new data frames. Data frames needs to be preceded by a diffs time of idle medium. So if this is longer than a SIFS, a data frame can never win against an ACK frame, right? So for 802.11 with 20 megahertz channel spacing, this is a typical Wi-Fi setup. Then the slot time, this time is 9 microseconds. The SIFS is 16 microseconds, and the diffs is 34 microseconds. So, so 9, 16, and 34. Numbers are not important except that they are related like this. A data frame is typically much longer than these periods, so this is not drawn to scale. Right? This could easily be, half a millisecond or something like this. 500 microseconds. Okay, but let's take a break for 15 minutes so we can resume 20 after the hour here.